Hey guys, so today we're going to go over how we determine the concentration of different solutions. We're going to be looking at a bunch of different types of concentration, a bunch of different ways of measuring concentration. There will be different calculations for all of those, but we are going to save the most important one for last. Molarity is the concentration that we're going to be using the most as we go through the rest of this course. That's the last one we're going to do today, definitely the most important one. So like I said, this lesson is on concentration. We are going to be going over percent concentration, mass percent, molarity, percent volume, parts per million, bunch of different types of ways of measuring concentration. You need to be able to calculate the amount of solute if you're given the concentration and the amount of solution. You also have to be able to calculate the amount of solution if you're given the concentration and the amount of solute. And then lastly, for our molarity calculations, you also have to be able to convert between mass and moles. So concentration is the measure of the amount of solute in a given amount of solution. Another way of saying that is that it's the ratio of solute to solution. If your solution is really dilute, that means you have a small amount of solute per your volume of solution. If it's really concentrated, then you would have a large amount of solute per your volume of solution. It is important to note that all of our concentration calculations are based on the amount of solute and solution, never the amount of solvent. So the first type of concentration is percent concentration, which is often used on like consumer products, the stuff that you would buy at the store, like vinegar and hydrogen peroxide. This is used anytime you're dealing with a liquid. So you have a volume of solute and solution. So sometimes we call this percent volume per volume concentration. We just take the volume of our solute, so the volume of the stuff being dissolved, divided by the volume of the total solution, and then multiply it by 100 to turn it into a percentage. This can also be used with mass. If you have a solid solute instead of a liquid solute, then it's percent weight per volume, where you have the weight of the solute divided by the total volume of solution, and then once again, multiply by 100 to turn it into a percent. Mass percentage works very similar. This is just when your solution is being measured as a solid rather than as a liquid. So in this case, our mass percent is just the mass of the solute, the stuff that you're dissolving, divided by the mass of the total solution. Once again, multiply by 100 to turn it into a percentage. Just make sure that your mass is the same units for both solute and solution. Doesn't matter what those units are, as long as they're the same as each other. So we'll go over the first of these calculations together, and then you guys can try the next three on your own. Okay, so for the first question, it says, what is the percent concentration of a 40 milliliter solution that contains 7 milliliters of solute? So because both of these are in volume, both our solution and our solute are measured in milliliters, we are going to be using this formula right here, the one where both of them are in volume. So the volume of the solute divided by the volume of the solution times 100. So all we're going to do is our percent concentration is equal, and I could write V per V here or whatever. Our percent concentration is just going to be 70 divided by 40 and then multiply by 100. So 7 divided by 40 is 0.175. And then if we times it by 100, we get 17.5%. And that would be our answer. So try the next three on your own. Pause now to do that and then come back to check your answers. Okay, for the next question, we're given our percent concentration, which is 4%, and we're asked to find the weight of the solute. We're also told that the volume of solution is 230. So I plug it into my equation. I, of course, have my times 100 here. Our very first step when we're doing this is to move the 100. We're trying to isolate the W, that's what we're trying to solve for, so we need to get it by itself, which means moving everything else away from it. When we do that, when we isolate a variable, we always have to start by moving whatever is furthest from the variable and then move closer to the variable. So I start by moving this 100. The opposite of times 100 is divide by 100. That'll cancel out. What I do to one side, I also have to do to the other. That leaves me with 0.04 equals W over 230. Now, if you want, you could have just started at this step. Many of you know that when you're dealing with percentages, you often convert them into decimals when you're doing math with them. So you could have just done that right away and then ignored the 100 and just started with this equation. But now that we have it this far, once again, I need to isolate the W. Anytime I have a fraction like this or a division happening, the thing on the bottom has to be the thing that moves. Because it's division, we use the opposite operation to do that. So I times by 230, that'll cancel out. And of course, what I do to one side, I also have to do to the other. So I multiply the other side by 230. 0.04 times 230 is 9.2. So that would be my answer. Okay, this time, once again, I'm given my percent concentration, so 15%. Your percent is always going to go on the left-hand side. Then I'm given my volume of solute and asked to find my volume of solution. And of course, I have my times 100 over there. I get rid of that first by dividing and gives me 0.15 equals 33 over V. Again, you could start with this step if you wanted, if you just know to convert your percent into a decimal and ignore the 100. This one's a little bit trickier because our V, our variable, is on the bottom of this fraction. And as I said in the previous question, when you have a fraction or division happening, the thing on the bottom has to be the thing that moves. So I have to multiply by V to move it to the other side. That leaves me with 0.15 times V equals 33. And now I need to get the 0.15 away from the V. Because this is multiplication, in order to move the 0.15, I use the opposite, which is division. So I divide by 0.15, that cancels out. What I do to one side, I must also do to the other. 33 divided by 0.15 is 220 milliliters, is our volume of solution. The last one deals with mass percentage. Once again, it gives us our percent, so that's going to go on the left-hand side. It also gives me my mass of solute, and it wants to know the mass of the solution. Of course, I have my times 100 there. Step one, get rid of the 100, move it to the other side by dividing. That gives me 0.06 equals 12 over the mass of the solution. Once again, when I have division, the thing on the bottom has to be the thing that moves. So I multiply by m to move it to the other side. That gives me 0.06 m equals 12. Now I need to get the m by itself. So I need to move the 0.06 away. In order to do that, I divide by 0.06. And 12 divided by 0.06 is 200 grams. That's your answer. The next type of concentration is parts per million, which is usually used when we're dealing with environmental contaminants. It's really only useful if you're dealing with really, really dilute solutions and very, very large solutions. So usually you're talking about things like lakes, oceans, groundwater supplies, that sort of thing. The concentration is measured by comparing the mass of the solute to either the mass or the volume of the solution. The trick is that the solute has to be measured in milligrams, while the solution is measured in either kilograms or liters. Or you can use a formula that multiplies your answer by 10 to the power of 6, but a lot of people don't like using exponents. If they're both in grams, you can, however, use the formula with the 10 to the power of 6. So these are the different formulas here. All of them are calculating parts per million. One is dividing the mass of the solute divided by the mass of the solution. Again, where the mass of the solute is measured in milligrams and the solution's mass is measured in kilograms. You could also calculate parts per million by dividing the mass of the solute in milligrams by the volume of solution in liters, or you can divide the mass of the solute and by the mass of the solution, with both of them being measured in grams, and then multiply your answer by 10 to the power of 6. And just don't forget how to convert between different units, since you do need specific units. This is King Henry drank Gatorade during Christmas Mass. King Henry drank liquor during Christmas Mass, where these are like kilograms, grams, milligrams, milliliters, liters. Those are the ones that you really need to know. Anytime you move between these, you're moving one decimal place. So let's try a couple of these calculations. Again, we'll go through the first one together, and then you guys can try the next two on your own. Okay, so for this first question here, it says we have a 1.4 liter sample of water, and it's found to contain 120 milligrams of mercury. What is the concentration of the solution in parts per million? So for this one, we are going to be using the second formula here that deals with milligrams and liters. Yep. So our parts per million is just going to be our milligrams divided by our liters. And we get 85.7 parts per million. So pause here, try the next two questions on your own, and then come back for the answers. Okay, so the second question says nitrates can end up in water due to fertilizer runoff and leaking septic tanks. Nitrate contaminated drinking water can be harmful to infants and lead to blue baby syndrome. Nitrate concentrations must remain below 10 parts per million in drinking water for it to be deemed safe. What is the maximum mass of nitrates that can be in 250 milliliter sample of water in order for it to be safe to drink? So right away, I see that they're asking for mass of nitrates. So we're going to be using the second formula again, the mass of nitrates with the volume of water. But of course, our volume of water has to be in liters. And in the question, it is in milliliters. So I'm going to write out my King Henry drank liquor during Christmas Mass, and I'm moving from milliliters to liters. So 1, 2, 3 spots to the left. So I'll take my 250 milliliters, put in my decimal, and move 1, 2, 3 spots to the left. So it's 0.25 liters that we're actually dealing with here. Then I'm going to write out my formula. So parts per million is going to be my mass of my solute divided by my volume of solution. It tells me that the maximum parts per million is 10. I'm looking for the mass in 0.25 liters of solution. When I'm dividing, the second thing or the bottom of my fraction has to move, so I multiply by 0.25. What I do to one side, I must also do to the other. And 10 divided by 0.25, or sorry, multiplied by 0.25 is 2.5. So 2.5 grams is our mass. That is the maximum amount of nitrates. Okay, for this last question here, once again, we are given the parts per million, so 0.002 parts per million. This time we're also given our mass of mercury, which needs to be in milligrams, and it was given to us in grams. So if we have King Henry drank Gatorade during Christmas Mass, right now we are given grams. We have to move 1, 2, 3 spots to the right to convert it into milligrams. So I'll get my 0.2 and go 1, 2, 3 spots to the right. So it's going to be 200 milligrams of mercury. And we need to find out what our volume is. Once again, when we're dividing, the thing on the bottom has to move. So I multiply by V, which gives me 0.002 V equals 200. And then, of course, I divide by 0.002 to get the V by itself. And we are dealing with 100,000 liters of water. The last type of concentration is molarity, which is the most important type. It's also called molar concentration, and it's a measurement of moles per liter. The formula that you need to know is C equals N over V, where C is the concentration in moles per liter, N is the moles, and V is the volume, which must be in liters. So let's look at some of these different calculations. Once again, we are given a volume in milliliters, which is not the correct unit. So I'll write out my Kane Henry drank liquor during Christmas Mass. And I need to move from milliliters to liters. So 3 spots to the left, 620, 1, 2, 3. That is 0.62 liters that we will be dealing with. Then I'll write out my formula. So C equals N over V. I'm looking for the concentration. I was told that I have 1.6 mole of solute. And of course, my 0.62 liters is my volume. So 1.6 divided by 6.2 gives us a concentration of 0.258 moles per liter. Your units could be written like this as moles per liter, or it's equally correct to write it as a capital M. A capital M also means moles per liter. Or I could write it in square brackets. All 3 of those are ways of representing molarity, or our concentration in moles per liter. So you'll usually see, actually all 3 of these kind of used interchangeably. So make sure you recognize all of them. Okay, try the next 2 questions on your own, and remember, it's got to be in liters for your volume. Okay, so for the second question, again, we're using C equals N over V because it's given us our concentration in moles per liter. So I can plug that in. My 0.7 moles per liter is my concentration. I'm looking for my moles, and my volume was given to me as 280 milliliters. But once again, I have to move my decimal 3 spots to the left in order to get it into liters. So it's 0.28 liters. When I have a fraction like this, the thing on the bottom has to move away from my variable in this case. So I multiply by 0.28. And then, of course, what I do to one side, I must also do to the other. So 0.7 times 0.28 gives me 0.196 moles as my answer. And my unit is just MOL for mole. For question number 3, once again, we have C equals N over V. Our 2 moles per liter is our concentration. We're given that we have 3 moles of solute, and we're looking for the volume. Again, when we have a fraction like this with a variable in it, the bottom has to move. So I will multiply by V to move it to the other side, which gives me 2V equals 3. And then, of course, to move the 2 away from the V, I have to divide. 3 divided by 2 is 1.5, and our units for volume are liters. Okay, so those are your different answers for concentration. Now, sometimes you will be given mass, or you'll have problems involving mass, instead of being given moles or looking for moles. So this is where you have to think back to when we learned how to convert between grams, which is our mass, and moles. And we do that using the formula moles equals mass over molar mass. That is a very important formula. So for these next two questions, we're going to be using our C equals N over V formula along with our moles equals mass over molar mass formula. Remember, mass does have to be in grams, and your molar mass you get right off your periodic table. So let's go through the first example here together. Okay, so for the first question, it's looking for our concentration, our molarity, which would require us to use the C equals N over V formula. However, you'll notice that we don't have our concentration or our moles. All we have is volume at the moment. So you can't use a formula when you have two missing variables. So instead, our first step is actually going to be to use our moles equals mass over molar mass formula. And I actually shouldn't even say that's the first step, because first we actually have to find our molar mass of KOH. So step one is going to be to find the molar mass of KOH. To do that, we bust out our periodic table. So I'm going to look up potassium, which is K, on the periodic table, and it has a mass of about 39.1. 39.1, and there's only one of those. And then oxygen is about 16. There's also only one oxygen, so I'll add 16. And then hydrogen is about 1. There's only one of those as well, so I'll add that. So 39.1 plus 17 is 56.1. Now that I have my molar mass, I'm able to go to my moles equals mass over molar mass formula. I can plug in the 12 grams that I was given in the question and my molar mass that I just calculated, and I can divide. That gets me 0.2139 moles. Now, finally, I can go back to my C equals N over V formula because I now have a mole amount to plug in and the volume, the 2 liters that I was given. And I just divide those to get 0.107 molar as my concentration. So pause here and try the next question on your own and then come back for the answer. Okay, so for this question, it says how many grams of iodine must I use to make 1.3 liters of a 5 mole solution? So I'm given volume and concentration, which means this time I can start with my C equals N over V formula, plug in my 5 moles per liter and my 1.3 liters as my volume, and I'm going to solve for N. Multiply by 1.3 because it's on the bottom. What I do to one side, I also do to the other. 1.3 times 5 is 6.5 moles. Now that I have moles, I can convert it to grams using moles equals mass over molar mass. Of course, in order to use that formula, I have to know the molar mass of iodine. It's also important when you're given the name of a compound as opposed to its formula that you write out the chemical formula of your compound so that you know how many of each atom you have, because that's going to affect the mass. For example, iodine is not I, it's I2, because it is a Hofbrinkel or a diatomic molecule. So I'm going to look up the mass of iodine, which is 126.9, but I have to multiply it by 2 because there are 2 of them. So 126.9 times 2 is 253.8. Now my final step can be to use my moles equals mass over molar mass formula. I know my moles, I already found it, it's 6.5. My molar mass, I just calculated, and I'm going to find my mass in grams. Once again, have to move the thing on the bottom, so I multiply by 253.8 on both sides. and I get 1649.7 grams as my final answer. So just remember, you can always convert between moles and mass depending on what you're looking for and what you need. If you're using your concentration formula, you cannot use mass. It has to be in moles. So use these two steps to always convert between moles and mass. Again, this is a super important formula. All three of these are going to be used over and over and over again this year. So please make sure you let me know if you have any questions.